Here we have a pulley, and the pulley has a rope, and the rope is attached to this object over here. We're on an inclined plane. The angle is 30 degrees. So the mass of this object is 1.5 kilograms, and it slides with no friction. And the pulley has a moment of inertia of 0.75 kilogram meters squared. It's 0.75 kilogram meters squared and a radius of 50 centimeters. And the question is to find the tension in the rope. Okay.
So, draw my free body diagram.
Right. Good. So there's the normal force, the weight, and the tension force. That's good. There's no friction, so we don't include that.
So I would, I'm going to be using my Newton's second law.
That's right. So this is not a conservation of energy problem anymore. Remember, the conservation of energy is usually best when you're asked for the speed or the distance. But here we're asked for a force. Well, if you're asked for a force, you're probably best off using Newton's second law. That's right.
Okay, so then I need to find the x and y components of the weight.
That's right. We need to break the weight up into x and y components.
So
It's probably best to draw a whole new picture to do that, because you can see we're already running out of space there. Let's see, one thing we can do is we can actually calculate the overall weight, right? Why don't we just go ahead and calculate the overall weight? What's that going to be?
14.7.
Yeah, that'll be 14.7 newtons. That's just m times g. Good.
So x equals 14.7 sine of 30, and y equals 14.7 cosine of 30.
Good. So how do we know that? So here's our x component and our y component. By the way, which way is the x component pointing up and pointing?
Down.
Yeah. And the y component
Also down.
and in. Yeah. So the weight, the overall weight was pointing down. So each of the components should be pointing down. Now we can make a little right triangle here. So if this is 30, this would be 60, and this would be 30. Okay, and then you're right, the wy is adjacent, so you would use the cosine for that, and wx is opposite, so you'd use the sine. Okay, good. So let's see what you get for that. Okay, what did you get?
I got 12.7 for y
Right.
and 7.35 for x.
Good. Okay. Yeah, so if you're at all in doubt, it helps to draw a nice big picture here, and that shows us since the 30 degrees is here, y is adjacent and x is opposite, so that gives you the sine and the cosine. Okay, good. So that gives us that. All right, so we've broken that into components. Good.
So then I would use net f of x equals max, and the object is stationary.
Now actually, we can't assume that this object is stationary. Yeah, we know it's attached to a rope, but the rope is not necessarily holding it stationary. it could still be falling down the plane. So we cannot assume that this object is stationary.
Okay. So then my x force is, if I say that up the plane is positive, then it's plus t minus the x component, which is 7.35. Equals 0.5 x.
Okay, so it's good that you remember that the weight would be negative, because the weight is pulling us down. So that would be negative. Okay? All right.
So then t equals 1.5 times the acceleration in the x direction plus 7.30.
True.
And then I have two variables, so I would go to the y.
That's right. So let me give it the y. Now, I'll say this sometime here. It turns out that the y equation is not going to tell us anything interesting. You can work that out and you'll see all that the y equation will help you to do is find the normal force. You could use the y equation to find the normal force, but we don't really care about the normal force here. If there was friction, it would be helpful to know the normal force, because we know that the friction depends on the normal force. But since there's no friction, it turns out that the y equation isn't going to give us any useful information. So, we still need another equation. Where can we get that other equation from? Well, how many objects are there in this problem? Two. Remember that the objects are things that have masses or moments of inertia. You want to treat the things with masses or moments of inertia, which is the analog to mass as an object. Well, here we were given the mass of this block, but we were also given the moment of inertia of the pulley. So that's the big clue that we should also treat the pulley as another object. All right, so maybe we can go through together how to analyze the pulley here. Well, we have to identify the forces on the pulley.
The rope?
Yeah, that's the tension force. And notice that that's just going to be tangent. So it's just going to go in this direction.
And it also has a weight?
That's right. It would also have a weight that's pulling it down. And presumably there's some support force also that's keeping it up from the axle or from whatever there. So presumably exerted on the center of the wheel here, there's some weight that's pulling it down and some support force that's keeping it up. Let me show you how to think about that. So maybe I'll draw a bigger picture here. If I could draw a circle, that would be nice. Okay, still not a very good picture, but it's the best I can do. Okay, now, what are we going to be focusing on here for the pulley? Translation or rotation?
Rotation.
Rotation. This guy would be translating, but the pulley would be rotating. Well, what's the version of Newton's second law for rotation?
Oh, it's net torque? Or, yeah, net torque equals I times alpha.
Right, so we're not going to use net force X or net force Y here. We could, but they're not going to give us interesting information. The interesting information here is going to come from the net torque equation based on the rotation of this object. All right, so one thing we're going to have to do is identify all the torques on this object. Why don't we get the, oh, did I ever give you the handout on torque? No, I don't think I gave you any handouts before, so.